So, good morning, everyone. Anyone notice any patterns? Mason?
If you go diagonally up and to the right, the last digit in each number is up.
Wow, okay, so I see like 11 and then 2, so the last digit is 1, then the last digit is 2, the last digit is 3, last digit is 4. Okay, cool. That looks, that makes sense. Kyle, did you ever notice that?
I'm not sure if it's the same thing you said, but if you go diagonally this way, there are consecutive numbers and there is a...
Oh, so you're saying this way? Like this?
way.
Yeah, this diagonal, like this.
Yeah. So
There's
0,
consecutive
1,
numbers like 0, 1, 2, 3,
16, 17, 18.
16, 17, 8. Yeah, okay. Yeah, I agree. Dora?
In the first row, when you go down and add 5.
Okay, oh, so every time you go down in this column, every time you go down, you, yeah, whatever, you add 5, so 5, 10, 15. Okay, yeah. It looks like there's like 1 to 6 is also 5, right? Gareth?
It looks like going down, they're all mod 5 with the next one.
Oh, you think, oh wait, so say that again? They're all
like 16 and 1, if you did like the equals 5 to it, it would just come out with 1 at the end. So that's the remainder.
oh, like all the ones in a column are all have the same remainder mod 5?
Yeah.
Okay. That looks, yeah, I agree with that. I'll copy it over one. Who else? Someone else had their hand up? Adam?
I was just going to point out the last row also follows a different 5 rule, as much as the first one does.
Oh, the 4, 9, 14, 19? Yeah, that's true. Okay, anything else? Sure.
You think we should the rows going across or mod 4 in the same way? Like going down as mod 5.
Okay. So, you mean all the rows are all equivalent mod 4?
They're all 4 from something else in the row.
Right. Yeah. Yeah, I think you're right. Anything else? All right, so everything you all said is true, and I'll tell you kind of the secret of how I made this, which I think actually goes back to an observation Gael made, which is that, like, you know, for example, if you look at a diagonal like this, you get consecutive numbers like 0, 1, 2, 3. Well, here's the secret. What if you kept going? Well, you can't go off the bottom, so where should we go? Where's the 4? The 4 is actually up here. Right, so it basically just wraps around. So when I go off the bottom, I go over one row, or go over one column, and then I go down one row. But since there's no row there, I have to wrap back around to the top. So it kind of like comes in here. And then, well, I'm going to go off, I need to keep going diagonally, but I'm going to go off the right edge, so it wraps back around. So I maybe I should like, how to draw this. It wraps back around to here, right? 5, 6, 7. It wraps up to the top, 8, 9. And then it wraps around to the left side, 10, 11. 12, 13, 14, wraps around, 15, 16, 17. So actually, one way to think of it, and this is the way that I thought of it when I was making this picture, is we just start in the top left, and we just write consecutive numbers, and at each step we go, over one row, or like, over one column and down one row. But when we reach an edge, we just have to like wrap around back to the other side. So you could think of it like, this is actually on the surface of a donut. Always just to go around. Okay. But and if you think about it, well, maybe we'll come back to some of the other observations you made. And all those observations you made are true, and we could kind of figure out why those things are true based on the procedure that I just described. But I also want to think about the fact that I find it kind of interesting that we just started in the top left and we just kept following this procedure, and we ended up filling in every single square in the whole grid, right? And the question is like, will that always happen? Or if not, when will that happen and when will it not happen? So I guess at this point, I am open to your ideas. So if you want me to, if you think, I think, it will. So I guess the question is like, if we do other sizes of grids, right? So this is like a 4x5 grid. If we did other sizes of grids, will this procedure always fill in all the squares, or not? And if not, can we kind of figure out when it will and when it won't? So if you think you know the answer, or if you're just like, can you try? Let's do a this by this grid and let's see what happens. What do you want to do? Yeah, Grace.
What exactly is the determinant for where it wraps around?
Just when you get to an edge. So in this example, like we started at the top left, and every step we go down and to the right. And so down to the right, down to the right. And at this point, I can still go to the right one step, but I can't really go down, right? Because I'm at the bottom. And so instead of going down, I wrap back around up to the top. But I still go right because like the 4 is to the right of the 3.
But like, I'm trying to figure out like, why does it end up where it does on top?
You mean why do we go from the 3 up to the 4?
Yeah.
Here's one way to think of it. Maybe this is a helpful way, I don't know. Actually, let's use like a gray or something. Imagine that like, we actually make a bunch of copies of this grid all around it. So like, a bunch of, like down here, we would make an identical copy of the whole grid. Right over here, we make an identical copy. This makes sense, and then over here, this would be like this side be copied. In other words, I take this 4x5 grid and I just like stamp it everywhere throughout space forever. And so now we can see that if I draw a diagonal line here, right, if I keep going, it goes to this 4, right? So one way to think of it is we actually are just drawing a very long, straight diagonal line through all these copies. Another way we can think of it is just like, we just have this one grid, and when we go into a copy, we're just like, well, really that's the same thing as if we were up here. Does that help? Does that make sense? Yeah. Good.
I just made a 7x7 to try it.
Okay.
The first thing I noticed is that if you just go down the middle line, it moves back onto itself. So
Yeah, okay. So I don't want to draw a 7x7. Let's just, if we do like a 3x3, the same thing should happen, right? So if we do a 3x3 grid, and we say, all right, we'll start in the top left, 0, 1, 2, where do we go now? So here's our diagonal line. What would be the next square after this? We actually have to wrap around both in rows and columns. So it would actually wrap around like just back to up here. Or if you imagine, you know, if you imagine making copies of this everywhere, there would be another copy of the whole thing right down here. But, so in this case, we actually do not fill in the whole grid. Right? We only fill in those 3 squares, and then we're stuck. We've already filled those in. Okay? So, all right, we already answered the question. No, we don't always fill in all the squares. But let's still see if we can figure out when do we fill in the squares and when do we not. So, other things you want to try? Mason?
Would it work, since that one up there's like a 4 by 5,
Yeah, I mean, if we just like flip our heads this way or something, I mean, it should. I think it would be the same thing, right? Yeah, I mean, if you flip this kind of this way, like you would still be going diagonally this way, but it would kind of do the same thing, just flipped. So yeah, I think, you know, you can convince ourselves through some sort of like, you know, flipping the paper over, looking through the back, you know, something that doing an m by n, it should kind of be the same up to some reflection as doing it n by n, or whichever is the opposite way. So. Okay, what else? What else you want to try? Yeah, what else? That is an interesting question, but there's a specific reason that I'm doing an offset of 1. So I'm going to stick with that for now. But maybe we can come back to that later, because that is an interesting question too. Garrett?
If we make it like, with a difference of 2 between this by this, like a 2 by 4,
Right.
also be second on itself.
Okay, so you're saying a 2 by 4. So you're saying this doesn't fill up the whole thing, so we start here at 0, and we go here to 1. We now wrap up to the top, and we get 2 here, 3, and then we're now going to wrap back around to the beginning again, so we don't fill it. And so, Gary, you're saying you think that's going to happen anytime that the rows and columns are different by 2?
I think that is right, but if I had to guess, I would think it would have something to do with the fact that you can think of that 2 by 4 as made up of like 2 blocks of a 2 by 2, which we already know doesn't work, because
Right.
it's looping back in on itself. So
Right.
like, you know, a 7 by 14 would also not work, because it would be made up by a 7
Right.
and a 7 and a 7 and a 7.
Yeah, well that makes sense, right? A 7 by 14, I'm not going to actually draw the whole thing, right? But if this is a 7 by 7, we're just going to get 0, 1, 2, you know, down to like 6 here. And then it's going to loop back to the top here and do 7 through 13, and then it's going to loop back. So yeah, I agree. What about like, let's do like 3 by 5, how about that? Here's a 3 by 5, this is a 4 by 5. Let's see, so 0, 1, 2, wrap around, 3, 4, 5, wrap at the top, 6, 7, 8, 9, 10, that actually works. Other thoughts or things you want to try? Have we done we haven't done 4 by 6, have we? Let's do 4 by 6, because that doesn't fall into this kind of pattern, right? But many people think it's gonna work? Gary thinks it's gonna work. Okay. 0, 1, 2, oops. 2, 3, wrap around to the top, 4, 5, wrap around the left side, 6, 7, this is looking pretty good so far, 8, 9, 10, 12, now we wrap back around to the start. Doesn't work. By 5, just check. This is 2 by 4. This is double. By 3 is also double.
So can our height and width not have any common divisors?
Okay, so Mason is suggesting, does it have to do with whether the height and width have common divisor? So do all the examples we've done so far, so what you're saying,
So like 4 and 5, and 3 and 5, those don't have any common
right,
divisors.
so 4 and 5 and 3 and 5, right, they do not have a common factor. And you're saying, in that case, it is possible, but if they share a common factor, then you think maybe it's not possible? So like 2 by 4 share the factor of 2, right? 3 by 3, obviously they share 3. 4 by 6 also share a factor of 2. Yeah. I mean, is there another size you might want to try that might give us some evidence whether that is true or not? What do you think?
I won't make them too big, like 5 and
5 and 9, all right.
We should be made up of like 3, 5, 3. We've already done 3 by 5. So we know that the first one works. I'm pretty sure we know that the second one works as well. It's like, if we add
5 by
together
3,
ones
I
that,
see.
if we add together ones that don't work, like a 2 by 2, a 2 by 2, and a 2 by 4.
I'm not sure, I don't know that putting together a 3 by 5 is quite the same thing as doing a 9 by 5. I'm not, you might be right, but I'm not sure about that. So let's, I don't know, I'll do it, and we'll, I'll do it quickly. Oh, how do you evenly divide things into 9 by hand? Do my best. Oh, like that.
I would do it.
All right, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This looks like it's going to work. It's not going to work if I skip it over. Oh no, oh no. I'll do.
Technology back then.
Works. Let's do one more. Let's do like 13 by 41. No, I'm just kidding. What do y'all think? Do these ideas sound reasonable? Obviously, we're never going to prove it just by like trying lots more things, but but it turns out, yes, this is true, and this is actually more than just kind of a curiosity. So, let's see if I can, there's a different way to think about what we're doing that connects it back to other stuff that we've talked about. And that makes it suddenly realize that this has much more fundamental importance than just a silly game about filling in grids of numbers. So here's a different way to think about this. So let's number the rows and the columns. So in this example, this is like row 0, and I'm going to number them starting from 0. We'll see why in a second. Okay. So I'm going to kind of keep track of my current coordinates as I'm going. So I start at 0, 0, right? And then every step I add 1 to each coordinate, right? So 0, 0, then 1, 1, then 2, 2, then 3, 3, then 4, 4. The next thing, right, would be 5, 5. But I don't have a fifth row. And so conceptually, I could imagine just I go 5, 5, then 6, 6, then 7, 7, except the actual row that I'm on isn't going to be 5, 6, 7. It's going to be 0, 1, 2. So the way that one way that I can think about that is by, I'm taking the row coordinate and I'm doing mod 5. So I'm saying, I don't care about, like, once I get past 5, I don't care. I only care about the remainder if I divide by 5. Like I don't care how many times I've looped around. I just care kind of where I am within those 5. And then the same for the columns, right? So in other words, we start at 0, 0, and right at, I'll call it, step 0. So like the number that I write in the cell is like which step I'm on, right? And then at step, or each step, we add 1 to both row and column, which means at step, but we reduce the row index by, mod number of rows. And same for columns. So that means at step I, what coordinates are we at? Well, we would be at I, except we're reducing them both mod, whatever. We are at coordinates I mod R, where R is the number of rows, comma I mod C, which is the number of columns. Okay, so any questions so far? Does this make sense how I'm connecting this to? We're kind of counting mod R and counting mod C at the same time. And so, right, filling up the entire grid, right, means that every step from 0 to, well, what is the last number, by the way? Like, how do I know what number I'm going to get as the very last thing? Dora? Yeah, exactly. Right. So the number of cells I have, of course, is the number of rows times the number of columns, but since I'm counting starting at 0, I get minus 1. Right? So every step from 0 to RC minus 1 corresponds corresponds to a unique pair, I mod R and I mod C. And vice versa. Right, so in other words, well, I guess no, look at that. I won't write it down, I'll just say, one way to think about this, if you think about two different sets. Well, I will write it down. No, because I want to be able to talk about, look at the grid. Think about the set of all the numbers from 0 up to r times c minus 1. If I take one of those numbers and I say, all right, I'm going to take that number as input and I'm going to output the pair, if that number is I, I'm going to output the pair I mod R and I mod C. And that will take me to a pair of numbers where the first number is between 0 and r minus 1, and the second is between 0 and c minus 1. That function is a bijection. It establishes an exact one-to-one mapping between, all these numbers from 0 to, in this case, 0 to 44, and pairs of, row column index. We can also think of it the other way, right? If I say, I'm thinking of a number, and the number I'm thinking of is equivalent to 2 mod 5, and it's equivalent to 6 mod 9. Right? So if you divide my number by 5, you get a remainder of 2. And if you divide my number by 9, you get a remainder of 6. What number am I thinking of? Well, in that specific example, we can figure it out by looking up in this chart. Like, well, it has to be on this row, because these are all the numbers that give a remainder of 2 when you divide by 5. And it has to be in this column, because these are all the numbers that give a remainder of 6 when you divide by 9. And so the answer is 42. Or, it could be 42, or we could, if we add, as if we kept going, after 44, we could keep going with 45 here, and keep going, right? So if we added another 45, we'd get 87, and that number would also work, right? So anything equivalent to 42 mod 45 would be the correct answer to that. Okay. So, this leads us to something called the Chinese remainder theorem. I assume it's called the Chinese remainder theorem because some ancient Chinese person wrote it down. I don't actually know. It'd be interesting to look up the history there, but I will state the theorem, and then we'll pause to think again about how this theorem corresponds to what we did with the grids. So let GCD of well, here I'm going to say M and N, or we could say RC, but so M and N don't share any common factors. That is, their GCD is 1. And I have some, A and B, which are integers. Then the system of equivalences x is equivalent modulo m to a, and x is also equivalent modulo n to b. Right, so this is like what I was saying before, where I said I'm thinking of a number, and its remainder, when you divide by 5 is this, and also its remainder when you divide by 9 is this other thing. And we saw that in the case of 5 and 9, right, anything like that that I said has a solution because every single square in that grid is filled in, right? But for some other things, like if I said divide by 2, remainder when you divide by 2, and the remainder when you divide by 4, like not every, in a 2 by 4 grid, not every square was filled in. So there's some combinations that don't actually have a solution. For example, if I said, oh, my number is odd, the number I'm thinking of is odd, that is when you divide it by 2, you get a remainder of 1. But when you divide by 4, you get a remainder of 2. That's not possible, because any number when you divide by 4 and you get 2, a remainder of 2, it's going to be even, so you can't have them both. But this theorem basically says that, yes, if m and n don't share any common factors, if the rows and columns don't share common factors, then it always has a solution. So, then the system of equivalences has a unique solution. Well, it's not absolutely unique, but it's unique modulo mn. That is, if you just look at numbers from 0 up through mn minus 1, there's going to be exactly one of them that makes it, that works. Questions? One remark that I could say. So we haven't proved this yet. I mean, we kind of maybe intuitively believe it from our investigation with the grids. So one way to think of this is, one way to think of this. Basically, we can replace the above pair of equivalences. So if I have two equivalences like this, we can replace it by a single equivalence of the form x is equivalent modulo m times n to some c. The theorem tells us there is a c such that, you know, this is true exactly when those two things are true. But that means, you know, because you might wonder, well, what if I have three equivalences and I want to solve all of them at the same time? Right? Well, actually, I mean, this theorem is enough to be able to do that, because we could then iterate this process to solve systems with, you know, more than two equivalences. Right? As long as all the you know, the modulos, the moduli, I guess is the word. As long as none of them share any common factors at all, right? You can just say, all right, let's just take the first two. This theorem tells me I can kind of squish those down into a single equivalence, and then I can take that one and the next one and like squish those into a single one. Now, the theorem doesn't actually tell us how, it just says there exists a solution. It doesn't tell us what the solution is. There are ways to find it. So I guess I'm trying to decide. Yep. But I'm not going to write down a formal proof of this. So again, our playing around with the grids hopefully gave us an intuition as to why this works, or makes us believe that, yeah, this probably works. If you want to read a proof, I think there's actually not a proof written in the PDF lecture notes, but there is a link to a proof. So if you want to read it, do that. But I want to show you, we've got maybe like 10 minutes left, and I just want to show you how we can actually, given that we know a solution exists, I'll show you one technique for actually solving a system of equivalences like this. So it's not really an example because, well, I guess it's sort of an example. It's an example slash, I'm not just applying the theorem, I'm going to show you a way to solve. So if we have x is equivalent modulo 5 to 1, and x is equivalent modulo 6 to 2. Well, one thing, let's see, here's what we're going to say. Since x is equivalent modulo 5 to 1, what does that mean? That means that x is 1 more than some multiple of 5, right? So that means x is 5 times t plus 1 for some integer t, right? That's just a different way to say the same thing. Substituting for x in the second equivalence. Okay, so I've got this expression for x, 5t plus 1. I can substitute that into the second equivalence. And that gives us 5t plus 1 is equivalent modulo 6 to 2. And I can try to solve this for t. So this implies, let's see, 5t is equivalent modulo 6 to 1. We could use, at this point, right, to solve this, we have to divide, quote, quote, divide both sides by 5. In other words, we have to find the modular inverse of 5, mod 6, and we can multiply both sides by that. We could use the extended Euclidean algorithm to do that, like we did last class. However, I'll do a shortcut in this case. Notice that 5 is the same as negative 1 for working mod 6. Yeah? Because negative 1 and 5 are different by exactly 6. So, obviously, the inverse of negative 1 is negative 1. You multiply negative 1 times negative 1, you get 1. So that means that 5 is its own inverse of mod 6. So I'll say 5 is its own inverse of mod 6, since 5 is equivalent to negative 1. So we can multiply both sides by 5, and that'll get rid of the 5. We can also just, 5 times 5 is 25, and that's 1 more than 24, which is a multiple of 6. So that means t is equivalent modulo 6 to 5. So we can multiply both sides by 5. Okay. Now what? Our ultimate goal is to find a solution for x, right? X is 5t plus 1. So at this point we can say, hence, t, well, t we know is 5 more than a multiple of 6. So we could say t is equal to, 6u plus 5 for some integer u. And we can substitute this back into x equals 5t plus 1. We get that x is 5 times 6u plus 5 plus 1, which is 30u cubed plus 5 times 5 is 25, plus 1 is 26. Make sense? Well, what is u? I mean, u was just any arbitrary integer. We don't know what it is, but it's just some integer. So if x is equal to 30 times some integer plus 26, that means that any number that's 26 more than a multiple of 30 is going to work. So this means solution is x is equivalent modulo 30 to 26. And that makes it makes sense that we're doing modulo 30, right? Because we started out with two equivalences, mod 5 and mod 6. And the theorem, the Chinese remainder theorem, tells us there should be a unique solution modulo 5 times 6, which is 3. And so that kind of came out of when we substituted this 6u plus 5 into 5 times something, we got 5 times 6. You know, or the other way you could solve this one, these numbers are small enough, you could just draw a 5 by 6 grid and like fill in by diagonals and just look up, you know, row 1, column 2 and see what's there, and it would be 26. And we didn't do 5 by 6, did we? Oh, I should have done 4 by 5, and we could look up. You know, and if you had a system of more than one, if you had like a system of 3 equivalences, once you got to this point, you could just keep going, do that same process again. I guess it can be a little confusing keeping track of like what you're doing, because it's like, well, we make up these different variables and we substitute this thing back into that. I don't know of like a great way to remember it. It's just a process. And if you kind of think about, if you keep in mind what you're trying to do, right? Ultimately, we wrote down some expression for x in terms of an arbitrary integer, and then we used the for one equivalence. Then we used the other equivalence to figure out what that arbitrary integer had to be. It couldn't just be any old thing. It had to be, in fact, it had to be 5 more than multiple of 6, and then we just put that back in the original equation to figure out what x is. Cool. Any questions? Olivia?
Not exactly.
Okay.
Just processing.
Processing. Cool. So a couple minutes left. Let me just say, why am I showing this to you? Like, why do we care? I mean, it's kind of cool that we can solve systems of equivalences. That's kind of interesting. This has some practical applications. So one kind of direct practical application is, suppose you wanted to do. So actually, this will be like particularly relevant for those of you that are taking CSO right now, but it doesn't matter whether you're taking it or not. Suppose you wanted to do math with some really big numbers, and the numbers were so big that you couldn't represent them in your computer. Your computer can only represent numbers up to a certain size, but you want to work with numbers that are bigger than that. One interesting thing you can do, right? But let's say that I do have a bound on my numbers. They're only up to like this big, but I can only represent numbers that are this big on my computer. You could pick 2 or more moduli, 2 or more numbers that don't share any common factors. And you could say, instead of directly working with these big numbers, I'm just going to look at the remainder, mod each of my, so maybe I pick 5, 6, and 7. I mean, those are very small, but like, just for an example, right? So instead of working directly with, 538, I look at 538 mod 5, and 538 mod 6, and 538 mod 7. And I now have 3 numbers that are all pretty small. And I can do math with them. So if I have two big numbers that are represented by these triples of remainders, to add them, I just add the corresponding things. To multiply them, I just multiply corresponding things. and I add and multiply mod, you know, like the first numbers I add mod 5, and the second numbers I add mod 6, and I add mod 7. So I always just have these triples of numbers where one is from 0 to 4, one is from 0 to 5, one is from 0 to 6. And then at the end, I can use this kind of technique to go convert back to my really big number at the end. And you know, that works. You can do that, and that is one potential way to represent you know, numbers that are too big to go in your computer. You can represent them by a set of smaller numbers and work with them, and then when you're ready at the end, you can convert them. I don't know how often that is. I mean, I think that has been done. Usually, when your computer, like if you use like a, you know, like in Python can represent numbers that are really big, that are bigger than your computer can store. It doesn't do this. It does something else, but it could. This also, this is less direct, and it's not. It wouldn't be obvious to you why this is the case, but it turns out that this is one of the ingredients that goes into a lot of cryptography systems. Kind of the thing that makes them work. One of the things that makes them work is this fact that this kind of is what guarantees that you can uniquely decrypt something that you encrypt according to certain mathematical schemes. We're probably gonna. I think we need to move on to the next topic on Monday, but you know, maybe if we have, there's like an extra day or something towards the end of the semester, one thing we could do is come back and talk about like how certain kinds of encryption work, because it is interesting to see how the math kind of fits together. All right, cool. So there should be a new module out pretty soon, and have a good weekend. See you all Monday. Yeah, just like